All right. So this is our last meeting here. I will be sending some more information via email regarding your group projects. We will be having the Blackboard discussion poster session for the group projects. And so I will be sending information within 24 hours, giving you instructions about how to upload your projects and etc. to the Blackboard forum. So yes, be expecting that information here in the near future. Today, the goal is to go over some last few things from ANOVA, and then we'll go over the test. A little bit, give you a little study guide for the test. So we've been going over this example. This is what we did last time. We calculated for this example F for a one-way ANOVA. Remember, one-way ANOVA is comparing these three conditions. It's comparing the means of these three conditions. So the means of our three conditions are here, 4, 1, and 1. And we calculated an F ratio of 11.25, which we got because we took 15 divided by 1.3 repeating. And just so we remember, that 15, which is called the MS between, the numerator of the F ratio, is basically something which measures the magnitude of the difference among these three condition means right here. The MS within, which is in the denominator, measures the average amount of variability within each condition right here. So in example 1, we got an F ratio of 11.25. In example 2, I changed the numbers. So you notice how the means of these three conditions for example 2 are different. It's 4, 4, and 3 now instead of 4, 1, and 1. And so the magnitude of the means is instead of being far apart from each other, the means are relatively more squashed together. 4, 1, and 1 are further apart from each other than 4, 4, and 3, which are relatively close together, which is represented in the fact, which is right here, the MS between has gotten smaller. In example 1, when the mean differences were 4, 1, and 1, relatively more spread apart, the MS between, the numerator was 15. Here now, the MS between is smaller because the difference between the means, the magnitude of the difference between the means has gotten smaller as well. That's the MS between. The MS within for this example, example 2, is the same. It has not changed. It's still 1.33. It was the same for example 1, 1.33. The reason is because, well, for one, condition 1, literally these numbers are exactly the same to give us a mean of 4. For this condition right here, the mean has increased to 4, but the way I did that, the way the mean got from 1 to 4 is I added a constant number, 3, to each of the original numbers, which in the original numbers are shown here. So I added 3 to each of these numbers to get these numbers right here. And so I'm adding the same number to each of these original scores to produce these, which keeps the variability within this condition the exact same as it was in example 1. Similarly over here, originally the mean for example 1, the mean of this condition was 1. Now it's 3. The way that happened is I added 2 to each of the scores in the original example, and that increased the mean of this condition to 3, while keeping the amount of variability within this condition the same. I mentioned last time, or someone was able to successfully answer when I asked the question, what would be the situation in which you had a mean of 5 scores that equaled 4, but they had the lowest variability possible? And the answer was, if you have 5 scores, which are all 4s, you have a mean of 4, and the variability would be 0. Similarly, you could have 5 4s over here, and then the mean of those would be 4, but the variability would be 0. Similarly, over here, you could have all 5 of these numbers equal to 3, in which case the mean of those 5 numbers would still equal 3, but the amount of variability would be 0. If that happened, if we had 5 4s here, 5 4s here, 5 3s here, the MS within would be 0, reflecting the fact that there would be no variability on average within each condition. All the numbers here were the same as the mean, all the numbers here being the same as the mean, all the number here being the same as their mean, would produce an MS within of 0. Here's the final example. And there's a question kind of pertaining to these types of things on test number 4. about the meaning of the numerator, ms between, and the meaning of the denominator, ms within. So for this example, it's like example 1. In example 1, the means of the 3 conditions were 4, 1, and 1. But if you look closely, you'll notice that I've changed the data up here. So this condition is exactly the same as it was in example 1. I haven't changed it at all. But I changed the numbers up here for the second condition and for the third condition to make it so that there's more variability. And I don't want you to calculate variance or calculate standard deviation here. I just want to kind of show you why or how it's apparent that there's more variability here. So I'm going to go back to example 1 real quick. If you look at the range of these numbers, the smallest number is 0, the biggest number is 3. So the range of these, this is example 1, the range of these numbers is 3. The mean is 1, the range of these numbers is 3, which means, there's some variability here. The range is 3. The range over here, 0 to 2, the range would be 2. So these numbers are relatively clumped close together, and these numbers are clumped relatively close together, especially compared to in example 3. If you look, I've changed the numbers now. The mean is still 1, but I've changed the numbers now so that the smallest number is -1 and the biggest number is 4, which means the range of these numbers is now 5. That means these numbers are relatively more spread apart in example 3 than they were in example 1. Similarly, over here, in the original example, the amount of the range was 2. Now the range would be -1 to 3. Now the range would be a difference of 4. The smallest number is -1. The biggest number is 3. That's a difference of 4. So the range is bigger here. These numbers are relatively more spread apart here in example 3 than they were in example 1, where they were relatively more clumped together. And so what this means is that there's more variability here in this example, in this condition, than in example 1. There's more variability in this condition compared to in example 1. So overall, if you take the average amount of variability in each condition, there's more in example 3 than there was in example 1, which you can see here. The denominator has gotten bigger. In example 1, the denominator was 1.3, reflecting the fact that the average amount of variability within each condition was relatively small. In example 3, I've made the variability in this condition bigger by spreading the numbers apart. I've made the variability in this condition bigger by spreading the numbers apart. And the net result of that is that the denominator, the ms within, has gotten bigger. And if you care, my calculations for ms within for this problem are right here. The ms within, therefore, has gotten bigger because the average amount of variability in each condition is the same. The ms between, 15, is the exact same as it was in example 1. Oops. In example 1, the ms between was 15 because we had 4, 1, and 1. The magnitude of the difference among these means gave you an ms between of 15. In example 3, you have the same exact means, and so you have the exact same ms between right here of 15. So these 3 examples, I've given you these 3 examples, and they're all very similar, but they differ a little bit in what the means of the different conditions are and what the average amount of variability within each condition is. And so you see how these 2 things, the size of the numerator, which measures the magnitude of the difference between the means, and the size of the denominator, which measures the average amount of variability within each condition. These 3 examples have helped to illustrate how these 2 factors affect the size of the numerator and the size of the denominator. How these 2 things, the magnitude of the difference among the means affects the numerator, and the average amount of variability within each condition affects the denominator. Any questions or comments here? Okay, I want to briefly talk about the F table. It's not too much different than what we talked about for the T table. We use it to look up critical F values. So I'll click on my F table there. Here's an F table, this red filled in part right here. I know it's a little small, but this basically represents the critical region. So if the F that you calculate is bigger than this critical F right here, so right here is a critical F. If your F that you calculate is bigger than that, you have a significant effect. For the current example that we're dealing with, let's look back at it. We have 2 degrees of freedom. Every ANOVA that you would ever calculate is going to have 2 degrees of freedom that you have to calculate. The degrees of freedom between, or the degrees of freedom numerator, is the amount of conditions, 3 in our example, -1 gives you 2. The degrees of freedom within is the total amount of people total sample size, 15 in the current example, minus the amount of conditions, 3. So 15 minus 3 equals 12. So degrees of freedom between, degrees of freedom numerator, or sometimes it's called the first degrees of freedom, is 2 for us, 3 minus 1. Degrees of freedom within, sometimes called degrees of freedom denominator, just the second degrees of freedom, is 12 because 15 minus 3. So 2 and 12 are our 2 degrees of freedom. So now we'll go to our F table and look up our critical F. So degrees of freedom 1, or the degrees of freedom numerator, is right here. That's 2. And then the other degrees of freedom is on here, 12. Go to where those meet, 2 and 12. Our critical F is right here, 3.89. 3.89 is the critical F. I should point out this is an F table for alpha equals 0.05. There are different F tables for different alpha levels. I just Googled this one, and there's different ones you could Google. Though you don't really need F tables in real life because SPSS will do all of this stuff for us. This is kind of how SPSS derives whether you have a significant effect or not, is using information like this that's stored in the SPSS programs. Once again, the row up here, these are the degrees of freedom numerator, the degrees of freedom between, or degrees of freedom 1. You look that up. For us, it was 2. The column right here is the degrees of freedom within, the degrees of freedom denominator, degrees of freedom, second degree of freedom, which for us was 12. Those meet up at 3.89. So the critical F for all of these examples, example 1, right here, the critical F would be 3.89. The F that we calculated, 11.25, is bigger than 3.89. So we would reject the null hypothesis for example 1. For example 2, the F that we calculated was 1.25, so that is less than the critical F of 3.89, and so we would accept the null hypothesis. For example 3, F was 5, which is just barely bigger than the critical F of 3.89, and so we'd have a significant effect here. Questions or comments about how to use the F table? Okay. If I recall, there's no F table questions on the test, though. So I want to show you a little bit about how to run a one-way ANOVA in SPSS and how to interpret the output, because there's definitely a question where you have to interpret the output for a one-way ANOVA on the written portion of the test. So here are the data for example 1 that the example 1 that I just showed you are showed here. This is a screenshot of my SPSS. So I have a column called score and a column called dummy code. All of the 15 scores from all 3 of the conditions are arranged in the same column. These first 5 scores are the no phone condition. The second scores are I think it's the hands-free phone condition, whatever the second condition was. And then the bottom 5 scores here are the handheld condition, I believe it is, the third condition right here. I've dummy coded it 1, 2, and 3. This is basically set up the exact same way as an independent samples t-test. The only difference is an independent samples t-test will always just have a 1 and a 2. It only has 2 conditions, whereas a one-way ANOVA will have as many different numbers that you have to dummy code as you have conditions. We have 3 conditions, so we have 1, 2, and 3 here in our SPSS. So you type things in right here like this into SPSS. The way you do it is you perform analyze, compare means, one-way ANOVA. This is a one-way between subjects ANOVA. You move the score into the dependent list. So you move this score into this list, and then you move the dummy code into the factor. And you can press options. And if you press options and then click to check, you can make it so that your means and standard deviations will appear. Otherwise, for a one-way ANOVA, the means and standard deviations don't appear unless you click options and then descriptive statistics. And then you would press OK, or sorry, you'd press continue, and then that would go away. And then when that goes away, you'd then press OK, which is underneath it right here. That would run the analysis, which would give you this output right here. I put red squares around the stuff that you really care about for APA formatting. So here's the F value is equal to 11 points. This is for example 1. Please note that the F value that SPSS gives you is the exact same as the F value that I calculated by hand and I showed you the answer to, 11.25. The degrees of freedom between is 2. I showed you that as well because of 3 minus 1. The degrees of freedom within is 12 because of 15 minus 3 equals 12. Those are 2 degrees of freedom. And then the P value, or the SIG P value right here is 0.002. This is significant. Can someone tell me how do I know that this is significant? What about this indicates to me that this is significant?
Because it's less than alpha.
Yep, it is less than 0.05, which is the typical alpha in psychology. And so 0.002 is less than alpha is 0.05, and so we have a significant effect. Please note that this is very consistent with what we just looked up on the F table. The F value that we calculated is 11.25. The critical F was 3.89. 11.25 is greater than 3.89, so we decided to reject the null hypothesis when we were doing it by hand. SPSS is giving us the exact same answer, of course. But with SPSS, we don't need the critical F. We don't need the F table because SPSS knows all the critical Fs and it can do the calculations for us. And so instead, it just gives us the p-value. And if the p-value is less than 0.05, less than alpha, then we have a significant effect, which is the same as basically looking up the critical F. And if your F value is bigger than critical F, then you have a significant effect. The p-value in SPSS tells us the exact same information. Here's how it's APA formatted, and there is, I believe, a question or two about APA formatting on the test, including knowing how to do APA formatting for T. Right here, I'm showing you how to do APA formatting for F. So you write the letter F, and then in parentheses, degrees of freedom between first, then degrees of freedom within second. So degrees of freedom numerator, or degrees of the first degrees of freedom, and then degrees of freedom denominator, or within the second degrees of freedom here. Close the parentheses, equals the actual F value that SPSS gives you. So it says F, then the degrees of freedom equals, and then the actual F value, comma, and then you write P equals whatever the P value that SPSS gives you. So you can see all I did here was take those things that I rectangled in the output, and I arranged them into the APA formatting here, and this is APA formatting for F. I sent you an email. Please note I sent you an email for how to do APA formatting for T. It's identical to this, except for T, there's only 1 degree of freedom. Otherwise, everything is exactly the same. Oh, and it's the letter T here instead of the letter F for T. So you'd write T for, if you're doing this for T, you would have T there, and then you just have 1 degree of freedom written in the parentheses, and then your actual T value, comma, P value, and then whatever the actual number for the P value was. So this is APA formatting for F, but I've also shown you before and sent you an email for how to do APA formatting for T, and you'll be responsible for both on the test. So now I'm going to.
Question.
Yes, please.
For the P, would it also work to put P as less than 0.05? Would that also work for APA? Can you do it either way?
Yes, you
Or would
can.
you rather put the actual value?
No, actually, I prefer that you put P as less than.
Okay.
I will accept what I did there, P equals 0.002. But in actuality, in actual published articles, you'll see P as less than. You rarely will see an equal sign there in actual published articles. So I prefer the inequality instead of the equality.
So if P is not less than, like if you're,
then yeah, you can put P as greater than, or you can put P
okay.
as equal to. Either one will always work.
Okay.
The reason why I don't like P as equal to is because sometimes SPSS gives you P equals 000, and I don't like it when P equals 0 because it's not, SPSS just gives you 3 decimal points, so it's not really, so it's not really that it's P equals 0. It just doesn't give you enough decimal points that you can see the non-zero numbers if it's a really strong effect with the small P value. So that's why I always prefer to say P is less than something, though I will always accept in this class P equals the P value.
Okay. And I actually have one other question, I'm sorry, about SPSS. So for, when I was doing the homework 5, it wanted me to have, like, when you go in on the variable view and you like put in the different, like scores and dummy code. It wanted me to.
Well, you do that. You do that in the data view, not the variable view. But yeah, go ahead.
Oh well, okay. It wouldn't work for me in the data view, so maybe I did it wrong. But I noticed that on for independent samples, it was a nominal variable was what you put, like with the little 3 circles.
Honestly, that nominal, the nominal versus scale variable usually doesn't matter.
Okay.
But sometimes it does, but it's very specific situations when it does, and it depends on, like, honestly, I would need to see your specific thing. So I'm happy to help you with that. But if you want me to look at that, can we do it like a private Zoom meeting after class?
Yeah,
I'll have time. We're gonna end early. All I have left to do is go over the test. So let's just wait until everyone leaves, then you can share what you have on your screen. Any other questions or comments? Good questions though. Any other questions or comments? Okay, so now it's time to go over the test. So I'm going to stop sharing. And then I'm just going to talk to you now. So I'm going over the test. There are 30 questions, and I'm going to go over some of the highlights here. Just going through it. So yes, there is a calculation, a couple calculations where you have to calculate T. There is a question here about pooled variance and what things influence the size of pooled variance. Now, you don't have to be able to calculate pooled variance. Like, we never actually did practice calculating it, but I talked about some conceptual things in class about what things influence the magnitude of pooled variance, particularly when sample sizes are different between two conditions. We talked about some of the things that influence the magnitude of the pooled variance. So check out that in the slides, maybe before you start the test. There's questions about confidence intervals, and these get most tricky for paired samples t-test and independent samples t-test. And I'll remind you, for both types of t-tests, if you have a confidence interval, you will have a significant effect if 0 is not in the confidence interval. For both independent samples t-test and paired samples t-test, the null hypothesis is so-and-so equals 0. And so if 0 is not included in your confidence interval for either of those types of t-tests, paired samples or independent samples t-test, then you have a significant effect. So don't forget that, because there's some questions about confidence intervals, and I want to make sure you understand the ultimately you determine, is 0 in the confidence interval for paired samples and independent samples t-test. If 0 is not in the confidence interval, you reject the null hypothesis. If 0 is in the confidence interval, then you accept the null hypothesis. There's some questions where it gives you like a little scenario, and you have to determine, in this scenario, should I use a one sample t-test? Here it calls it a single sample t-test, which means the same thing. A z-test, a paired samples t-test, or an independent samples t-test. So you have to basically know, when do I use each of the types of hypothesis tests that we've learned? We've learned z-test, single sample or one sample t-test, paired sample t-test, independent samples t-test, and one-way ANOVA. Those are the 5 hypothesis tests that we've learned. And you need to, they're all subtly different. You need to know when you would use each type. Yes. Okay, let's keep on going. This will be a tricky question, I think, so I really want to highlight it. There is a question about the relationship between the Z and T distributions. So I would have talked about this back in the chapter about one sample t-test and paired sample t-test, most likely. So I think I showed a picture where it shows the Z distribution, which is taller and thinner than all of the different T distributions. Remember, there's different T distributions depending on the sample size, but there's only one Z distribution. And the Z distribution is always taller and thinner than T distributions. But as T distributions get, as the sample size gets bigger for T, the T distribution, well, something changes about the T distribution. I don't want to tell you exactly because it was the answer to the question, but I want you to know, how does T distribution change as the sample size increases? And I talked about that in an earlier chapter. I think that will be a challenging question, so take a look at those slides before you start the test would be my suggestion. Yeah, there's some questions about APA formatting and how to determine whether a p-value is significant or not. We were just talking about that. There's some questions which require you to know information about MS between versus MS within. Like in this problem, is MS between big or is it small? You don't have to know how to calculate MS between and MS within, but you do need to conceptually understand in which situations will MS between be big versus small, and which situations will MS within be big versus small. We did some practice on that today and last class. Another confidence interval problem. There's a little bit about effect size. So review the stuff that we've talked about regarding effect size previously. Make sure you understand, you remember Cohen's D and what the different Cohen's Ds means, like the different measures of effect size, whether they're, you know, small, medium, or large, and what those numbers mean. Yeah, there's a couple things you have to be able to interpret SPSS outputs. Yeah, definitely some confidence interval problems. Yeah, that's about it. Yeah, I think that's a pretty good study guide. Does anyone have any questions or comments then about the test? All right, well, that's all I have planned. I'm definitely happy to talk with anyone who wants to stick around and talk. Otherwise, please be expecting information regarding your the group projects you'll be posting on the discussion forum over the weekend. So stay tuned. I'll be sending information about how to do that within 24 hours. Otherwise, I'll see you guys later.